Hello, our project is self-adaptive circuit. Our team number was 19. My name is Saikidla and my team member was Arpit Pathak. And this is our basically the presentation. So what is a self-adaptive circuit? So what happens is due to various reasons beyond our control, like changing temperature condition or changing voltage condition, supply voltage pressure, the circuit output changes. It's not the same that we were wanting to observe. So like power supply discharging and several other things happen which aren't in our control. So the aim of this project is to basically self-adapt the circuit without manually any changing and repeated maintenance, we can still get the same desired output for even the changing input condition. This is a great breakthrough since it will actually reduce the regular maintenance cost and it will have several other obvious benefits effects. So what do we self-adapt? So basically we choose a Colpitts oscillator. It's basically an LC based oscillator. So it has basically we choose this because we have two more domains to just self-adapt with which are the frequency and the peak-to-peak voltage. So it basically gives a sine wave with a particular frequency. When we increase the temperature or supply voltage, the frequency and the peak-to-peak voltage both changes. So now we have scope to change and observe and self-adapt both of them. We observe that as we change the supply voltage, there is a major change in the output voltage while the frequency doesn't change much, and this can be ignored for very practical purposes because the Colpitts oscillator has a very high frequency in the range of 250 to 350 kilohertz. So basically a change of 100 or 200 hertz doesn't matter much for us when we change the voltage. When temperature changes, the voltage changes, frequency changes significant. As temperature is varying, we saw a substantial change in frequency and voltage. So how do we self-adapt? The self-adapting process will involve first-hand knowing the current output, because we will need to know the current output of the circuit and the desired output as well, so that we can change the internal circuitry to get it back to the original output. So basically, what we do is we basically train a model from the data we collected. So we basically use a three-layer neural network which was highly accurate to predict the output. For the test data, we basically use a very high-end software which is called as micrograph. It basically allows us to manually put a temperature coefficient for inductor capacitor by calculating them manually, and then we can use this for the training purposes. So basically this is a Colpitts oscillator circuit. It's basically an inductor which has two capacitors connected to it in a parallel, because this capacitance and inductor collectively decide the frequency, and basically this BJT based circuit makes sure that we can amplify the output to get a desired peak to peak voltage. So basically the output has some DC component, we remove it with a DC block, or simply we can choose an high pass filter which also removes a low frequency as well. This is basically the model that we this is basically the simulation we observed. We The hardware that we made was very closely matching to our theoretical the working of the circuit. So as can be seen, basically it's an inductor with connected two capacitance. Basically we connect this tank circuit to an amplifier. This amplifier converts the DC signal as the input to an AC signal as output, like a square wave or a sine wave. And the variable frequency drive by using the positive feedback this is known as an oscillator. It is a very linear oscillator. We use a capacitive voltage divider. Frequency range can be from 10 kilohertz to 300 megahertz, and we use a BJT or BJT op amp to amplify the signal. We can also use a normal op amp, but we use a BJT based amplifier. What is a general AI workflow? So basically general AI workflow is that we have an input sample, we have an output sample, and we have a mapping function that f of x will give me y. So we basically train for this output sampling function. So we have the training data, we pre-process the data because the data has some irregularities. We need to clean the data first before just using them. We need to standard scale the data so that the data is more actually like the frequency ranges is from kilohertz. We cannot take like 250 kilohertz as an input sample because that will just lead to more errors in the epoch. So what we do is we standard scale the output to make the output range from -1 to 1. If the inputs are lower, the function that we get is also a bit more feasible, and we can just scale it back to get the correct output. So what happens is that we pass this training data to the pre-processing and the training phase. We pass this to the model. From the model we get the weight. This weights we can use to see the unseen data and validate the unseen data according to the prediction. The more the accuracy we get, the better it will be. This is the basic workflow. The collection of data for model training. So in the Microsoft software, technically there are no, we can vary the thermal coefficients if we want, but from by default there are no thermal coefficients. So what we did was we manually make some circuits on capacitance and inductor. We heated up the circuit, and at different values of the observed outputs, we found out what capacitance value should have been to get the same output. Now from this values we calculated the capacitance or inductor coefficients by this general formula, that is C equal to C reference times the 1 plus alpha times of T minus T reference plus beta times of T minus T reference whole square. So basically this is in general for any component we can calculate the thermal coefficient by this. Now from this because now it required us multiple reruns because of some limitation of the way we are heating the circuit and the way the things were cooling down, and we weren't knowing the exact temperature because the sensor cools down a lot faster compared to the things and the circuit. So we had a very approximate calculation which might not be very accurate. So there were some discrepancies in the model and the hardware. We then collected this data graph. This, as you can see, is the peak to peak voltage versus temperature graph. So as you can see, the voltage increases as temperature increases, and this is for different supply voltage in some step size. This from V1 equal to 5 to V1 equal to 8. So as voltage increases, the output peak to peak voltage also increases, plus as temperature increases, it also increases. You can see that it's actually a linear condition, which is very favorable for us because adapting linear things is very easy. This is a graph of frequency versus temperature. It follows some certain curve. I don't know, it actually doesn't fit into any proper polynomial. That is why we use a very proper model for it. So this frequency versus temperature, it also increases. We observe that even for different voltage values, the graphs are coinciding only. So changing temperature, changing voltage doesn't matter for the frequency much. So we ignored it because it was very small. Now the same thing that I was saying, the variation of capacitance with temperature, this is a graph we plotted from the coefficients we got. As you can see, that it is obtained from the manual calculating of the thermal coefficient and the range of the temperature that we worked on, that is 20 to 80 degrees Celsius. The capacitance steadily decreases. It's not very lean, it's not linear obviously, but it decreases. Same for the inductor can be said. So this is the plot for the inductor. So inductor actually varies very differently. Inductor, you cannot just like make it the same model the same way as capacitor. So it is the heating and the cooling effects. One of the two main reasons is the inductor not only has its own inductance due to the coil, but it also has an internal resistance. So the internal resistance varies as well, and we weren't able to model the internal resistance coefficient very properly, but still we were very close. This is the graph we get for the inductor. Basically training the ML model, what we did was we first tried out various of the regression models which are very common, like the linear regression, polynomial regression. We also tried XGBoost and a random forest regression. We get a low accuracy score. So we basically move forward for a 3-layer neural network with a 0.998 R2 score, that is 99.8% accurate, and a very small root mean square error, which is what we desired. We use some Keras and scikit-learn libraries for our model. The general neural network looks like the attached picture. So basically you have the input layer. The input layer makes some more relevant input features. So basically we can understand this by, let's saying that we have an example. Let's say that a product, you have, let's say, the cost and the material which is used. Now we can actually make a better parameter, cost and material. It's better to consider the affordability of the product and the luxury of the product. So if so it's a better parameter than cost and basically the thing as well. So basically we make better input features from this. This is the detailed expression of the model. So we read the data set from so this is the collected frequency data set. We collect the data set, we split the data set into train and test samples, then we standard scale, so that as I said, we can basically, the train data and the test data are having a very high value. So like a frequency in kilohertz, 250 kilohertz in the range of megas, that is 10 power 6. The chances of lesser accuracy in ML is very high. So what we do is we standard scale them to from -1 to 1 to reach a more feasible value, so that in the calculation the root mean square error will be very less. Then when you standard scale, the root mean square error will be staying the same only. Defining the model. So basically we tried for multiple layers. This is what we got. So we first have 3 layers. First layer is a 4-layer neural network. It will give 4 outputs. It will be a ReLU layer. So ReLU is basically max of 0, x. If the thing is positive, it gives x. If it's not, then it gives 0. So because we have standard scale, the values are now from -1 to 1. It's not like all the values are positive since the temperature is also increasing, voltage is also positive, output is the frequency which is also positive. No, it's not like that. Because of standard scaling, the things are now from -1 to 1. It's important to know that. Then we also have another ReLU layer and then a simple layer. The simple layer just outputs what is the input. We define the layer by ReLU, which is defined as ReLU of x equal to max of 0, x. This is the general diagram. What happens is that you have multiple inputs, you have multiple weights assigned to it. Then you get the transfer function, you pass it to the activation function, and you get the output. Then we compile and fit it into our data set. So we basically have an Adams algorithm. Adams algorithm is very similar to gradient descent algorithm. It has a learning rate of 0.02, and we use a measure of accuracy as basically the square error. We fit the model. We have batch size of 8. So what we are doing is we are taking 8 samples at a time, and we are running it for 300 epochs. And then the one with the maximum probability, we are taking it our answer. Then this can be observed as the error and the R2 score values. The mean absolute error is 0.0019. The root mean squared error is 0.0027. It's a very small error. The mean squared error is in 10 order of 10 power minus 6. As can be seen, it is a very less error. R2 score is 0.9978. So these are the weights and biases we got. How exactly do we self-adapt? Now the ML part is basically over. We have the output voltage, output features. We have the voltage output at this particular temperature, at this particular voltage supply. We have the output peak to peak voltage, and we have the frequency. Now we can easily self-adapt this. By our topology, what we did was we used a self-adapting voltage using an inverting amplifier, which is made by a OP27 high-speed op-amp. What happens is that we already have a connected buffer because of the DC offset and matching the impedance. We connected an inverting buffer. So inverting buffer already inverted our existing output. Now we have another inverting amplifier. So 2 times inverted, it will give the same output. Right. So for the self-adapting the voltage, we use an inverting amplifier, which is basically made using OP27 high-speed op-amp. We had a hard time finding the OP27 high-speed op-amp because of the lesser availability in lab. So basically, we have a frequency ranging from 250 to 300 kilohertz. So what happens is due to the very high frequency, the normal op-amp is not able to amplify it properly. Okay, the output values we are using our neural network. Let's say the predicted voltage is VRES, and let's say the desired voltage is V norm. So we can actually just arrange the gain so that V norm by reference equal to RF by RI. We can push the put the RF and RI values desirably and get a desired output. So just basically this op-amp based circuit has a gain of RF by RI. Okay, so what happens is that there's a standard, so the positive terminal is connected to ground, the negative also gets connected to ground due to the virtual ground effect of op-amp. Then you can actually just derive that by the Ampere's law. V in by Ri must be equal to V out by Rf. So V out by V in equal to minus of Rf by Ri. This is basically the principle of inverting amplifier. Now because of we can adjust the Rf and Ri, we can basically force the V reference to go down times RF by RI, and then we can get the V norm. That was the desired output voltage. We can basically adjust it. This is the first thing, and then the second is how do we adapt the frequency. So basically adapting the frequency here is also very simple. So in any LC oscillation based circuit, the theoretical oscillation frequency is given by 1 by root of LC. It's a very simple derivation. Now this C is basically the reduced capacitance. In our case, it is C1 C2 by C1 plus C2 or C2 C3 by C2 plus C3, which are the two capacitance which are acting as a voltage divider. So these are theoretical frequency. Now let's say as temperature changes, the capacitor and inductor changes its value. Let's say C2 is out of effect of temperature. What we are doing is we are not changing the C2. We are keeping C2 constant, and we are going to self-adapt the C2 only, right? So what happens, let's say, is that the C3 capacitance after increasing temperature becomes C3 dash, and the L1 becomes L1 dash. C2 is still remaining the same, and so what happens is that C3 C2 L1 by C3 plus C2 should be equal to C3 dash L1 dash by C3 dash plus X times of X, and X is the new capacitance I am putting instead of C2. What I am doing is I am replacing the capacitance C2, and instead we are basically making sure that the C2 is out of the temperature effect. So C2 will be same. Let's say the new value of C2 is X. So this equation should be satisfied. When this equation is satisfied, the frequency still remains the same. From this we can get the values of. The reason we are not varying the inductor, there is no limitation on varying the inductor as well. There are two problems. First of all, the inductor has an internal resistance. If we vary the internal resistance, what happens is the output voltage also changes, because output voltage also depends on the internal resistance of the inductor. So we cannot just directly change that. And the second problem is that we do not have a lot of values of inductor. So there will be always some hardware limitation for changing the value of inductor. We still have the hardware limitation with changing the value of capacitance, but it's relatively lesser. So if we choose such a capacitance such that this thing is satisfied, this equation is satisfied, we'll get the self-adapted as well, frequency as well as self-adapted. What were the limitations in this? The heating equipment, we were using basically a dryer. So the heating equipment was very inconsistent, and the temperature lags because the sensor heats very fast and the sensor cools very down faster. But the circuit doesn't cool very faster and doesn't heat very faster as well. So there were a lot of discrepancies when we are calculating the coefficient, and we had to multiple reruns for calculating the coefficient. The process of heating and changing the circuit causes the circuit to become hot, undesirable, or less or more hot and desirable. What is happening is that, let's say I am actually heating it. Now I'm trying to change the things so that it matches to the self-adapted output, but what is happening is the circuit is getting cooler than it was supposed to be. So basically my desired output will not be the same as I wanted. There will be some minor changes, not much, but minor changes. High frequency signals required a high speed op amp, as I already said, which we had a very hard way finding because we weren't aware. We read the op amp documentation of US741 and it has a bandwidth of 8 megahertz. So we thought that we would be able to use it, but there were some still problems. We used the OP27 and there was no problem then. The exact values needed to replace instead of the capacitor and resistor are not feasibly available due to the limited lab components. So capacitor, inductors, resistors and inductors that we have to replace, they're not easily available. One of the main reason is that what are the possible betterments? We can actually have an accurate temperature coefficient. This is one of the main thing because this is basically how we are training our sample, right? If the training sample set is inaccurate, then the output will be inaccurate and there will be inaccuracies in the self-adapted circuit as well. So if we have a very accurate temperature coefficient, we can get a very good circuit, and we can have a digitally programmable resistor and capacitor and inductor. What will they do? So we need a digitally programmable capacitance. What happens is that currently we are manually calculating the capacitance value and then changing it, and removing the capacitance, putting it, removing the resistance for the inverting amplifier and putting it. If you can instead have an basically an like a digital potentiometer, which can from our microcontroller we can vary the resistance, that it will be very more simpler and actually self-adapting circuit for us. So this was also due to the basically the inability of the components. This was actually our aim to use this, but not now. We still haven't planned to continue this, and in the future plans we will actually be using this to make a proper self-adaptive circuit. The one thing we actually ignored was the change in the phase. As temperature increases, the phase of the circuit also change, but detecting the phase but changing the phase of the circuit according to our mentor was very much out of the phase, out of the scope for us. We should first focus on changing this only. So if we get a opportunity, which we will probably make a phase shifter circuit. This phase shifter circuit will basically adapt to the way we want, and we'll actually make sure that also basically we still have an idea of how we are going to do it. We are going to use a simple phase shifter circuit. It has some resistance and capacitance. We will basically model how much phase has changed of our model as we increase the temperature or change the voltage. We have that phase change. We can provide this much phase change. We can calculate what values of resistance and capacitance we need to change the phase, and we can use that as well. And we want to make a basically a very completely self-deployable circuit. We don't want to like manually change things. We want it to be a very deployable circuit. So this is one of the major things that we plan to do. Thanks. So that's all we have. It was a very fun project. This is a very high research base and very high utility project. We will probably try to work more on it. Thanks.